Welcome back to Electronics, Simple Circuits and Measurements Fundamentals. In the previous module, we discovered the LED and discussed the importance of using resistors to limit the amount of current that is forced through an LED by a battery. Now, let's work through a second hands-on exercise to explore current-limiting resistors. Let's start with our goals statement. First, we want to make a circuit which will safely illuminate an LED using a current-limiting resistor. Then, we need to measure the current flowing through the resistor, so we can definitely ensure that the LED is operating within its limits. In this exercise, we'll use all of our components: the LED, a resistor, the 9-volt battery, the breadboard, and our multimeter. As we start the first part of our goal, let's clearly lay out the problem. First, we know that we'll use a current-limiting resistor circuit, which incorporates our 9-volt battery, an LED, and a resistor, linked one after another in series. Therefore, the unknown element is, what size resistor do we need to adequately throttle the current? To answer that question, we'll need to make some calculations. Take a moment to pause the video to determine which equation we need to use, and plug through the calculations to solve for our missing resistance value. So, which equation did we choose? Ohm's law seems appropriate. Let's plug through it. First, let's rearrange to solve for R. Then, let's plug in our known values. Earlier we mentioned that an LED can only handle 2 volts at 20 milliamps. Therefore, we know the current, I, is 0.02 amps. But what about the change in voltage? You may be tempted to plug in 2 volts, but why is that incorrect? The fact of the matter is that we're using Ohm's law to calculate the size of our resistor. Therefore, since we need 2 volts left over for our LED to shine, our resistor needs to consume the excess voltage. 9 volts minus 2 volts is 7 volts. We need to consume 7 volts with our resistor, leaving 2 volts left over for the LED. Running the numbers, allow me to round the results to 330 ohms. Why 330 ohms? Well, it so happens that resistors commonly only come in specific sizes. 330 ohms happens to be a common one, likely found in your kit. If you don't have a 330 ohm resistor, try to find something close to it, preferably something that is higher in resistance rather than lower. We'd rather be safe than sorry. Now that we know our resistor size, let's make our circuit. When hooking things up, what do we need to consider? Before you connect your battery, pause the video and take a moment to consider any pitfalls you may need to keep in mind. Let's do this. Arranging our components on our breadboard, we need to hook them up in series. Another consideration is the LED. Remember, if it's backwards, it won't light up. Use the diode check function on your multimeter to determine the proper orientation. Does it light up? If so, fantastic. If not, take a moment to compare your circuit to the diagram shown here. Finally, let's measure current. Recall that to measure current, we need to connect our multimeter in series. Take a moment to pause the video and do this yourself. We're in the home stretch. Let's splice in our multimeter. I'm going to place the multimeter in series after the resistor, between the resistor and the negative terminal of the battery. But you can splice in anywhere, since we know that the current is the same at any point in this circuit. When we switch our multimeter to current mode, A, we should see a value somewhere close to 0.2 amps. If you still can't get things to work, take a third look through your circuit. Confirm that directional elements, such as the battery and the LED, are oriented correctly, and that your resistor is of the proper size. Double check with the resistance mode on your multimeter. If you still don't see anything, it's possible that your LED is burnt out. Try swapping for a new one if you are absolutely confident in the construction of the rest of your circuit. Let's wrap this up by summarizing our takeaways. First, know your parts. We've seen resistors, breadboards, LEDs, and batteries, and there are so many other components out there to explore. Some of these, like LEDs and batteries, are polarized, meaning that their orientation is critical to their function. This is different than things like resistors and plain old wires. These elements work regardless of their orientation. Next, Ohm's law is key. Be sure that you memorize this simple relationship. It's essential for calculating resistor sizes and so much more. Finally, the multimeter is an incredibly useful tool for measuring electrical quantities of your circuits. Voltage is measured in parallel, while current is measured in series. This concludes our Electronics, Simple Circuits and Measurements Fundamentals Skill Building Workshop. If you'd like to learn more about this subject we've covered today, check out our additional resources that we have available on the ITLP website, or pay us a visit in the ITL laboratory. We'd love to chat and get you on track to success. Also, take a moment to explore our workshops catalog, where you can find more skill-building workshops that explore even more electronics topics. Thank you for your time, and we'll see you next time.